This is number 85 in chapter 18. It looks at the calculation of a cell potential using delta G's. So we want to use delta G's of formation to ultimately determine the cell potential for a particular process. And it says that we have a fuel cell that employs the reaction between methane gas and oxygen, and then that methane gas and oxygen form carbon dioxide and H2O as a gas. So we get that actually from the language of the question. They don't draw the equilibrium, they just tell that within the question. And so we need to use delta G's that we would get from a table in order to figure out what the delta G is, and then from that we can get at our cell potential, right? Because delta G is equal to negative NFE of that cell. And so one thing we have to make sure of is that we're balanced. And so in order to balance this process, one thing to start quick would be hydrogens. We need to have a 2 there, and then in order for our oxygens to balance out, we would need a 2 there as well, right? And then we can just use our delta G form, meaning that if we can just sum up the delta G's of formation of our products and then subtract off the sum of all those delta G's for our starting materials, we can get the delta G of the reaction. So I'm not going to review that whole process, but we would have to take our products minus our reactants, and so that's why it's critical that we have these balanced. The delta G for CO2 is negative 394.4, and then we'd have to take 2 times the delta G for steam, which is negative 228.6, and so those are our products. And then we're going to subtract off our starting materials, which is really just methane, negative 50.5. Remember, oxygen's delta G is going to be 0. And so we solve for that. We should get a delta G for this process to be negative 801.1 kilojoules per mole. Now that we have our delta G, we can use our equation, which I had above. But we can manipulate that to solve what we're actually looking for, right? And so our cell potential would be equal to our delta G that we just got over negative N and F. So one thing that we have to remember is that our Faraday's constant is that 96,500 coulombs per mole of electron. And so we also have to remember that our volts are in actually joules, right? Our volt is actually a joule per coulomb, right? So when we combine, this equation using our volts and our Faraday's constant in this delta G expression here, we have to realize that delta G needs to be not in kilojoules per mole, but in joules per mole. Because again, our cell potential is in voltage, and a volt is actually a joule per coulomb. So when we solve for this cell potential, right, that cell potential is going to be negative 801.1 times 10 to the third joules per mole over negative N, and we'll come back to that, and then we have the 96,500 coulombs per mole of electrons, which will ultimately give us our answer. But let's go back to N. We have to figure out what N is, and that comes in looking at the changes in our oxidation numbers. Our oxygen, which is 0, is actually being, reduced. It's being turned into water, And so it's going from a 0 oxidation number to a -2 oxidation number, so it's actually being reduced. The methane, the carbon of the methane is actually what is being oxidized, and the carbon here for methane is actually -4 for its oxidation number, and then in CO2 it's +4. So that transfer from -4 to +4, right, is a total of 8 electrons being transferred. And so we would have to balance that if we were to get a really good balanced reaction here. But really that's all we need to know in determining what N is, right? Because that number has to be consistent for both oxidation and reduction. And so we just need to plug that value in there. And then when we solve it, we get a value of 1.037 volts for the cell potential at standard state, again using delta G's from the table for the delta G of formation of products and starting materials.